and carried on to Oak Ridge and then onward from there. Now this talk was really originated for the U.S. Naval Academy midshipmen. They asked me to give a talk up there, and I called it Supercomputers, Past, Present, and Future. Well, then I went on to give some other talks over in Europe, and they knew I was from NASA. So if you're from NASA, it's a big attraction. They said, can't you add something on about NASA and some of the analysis? So the talk then started out as strictly supercomputers, but then I added on some things about analysis and some of the NASA missions that I've been involved with in the past. So some people ask what it's like to, be at NASA and then go on to a second career elsewhere. And what I considered it was, it was more like the main course was NASA Langley, and then Oak Ridge was the dessert. So it was very pleasant to move on to Oak Ridge, although I had very exciting things going on just before I left Langley too. I was at Langley for 35 years, 70 to 05, and then came to Oak Ridge in the Future Technologies group, which looked at the forward-thinking ideas towards supercomputers with accelerators. So I've been working at that at Langley, so they recruited me to Oak Ridge. So anyway, that's where we are. The next slide, I have one slide about kind of history if you don't know me, and most of you don't because I've been gone from Langley for a while. But I grew up on the prairies of Saskatchewan, of all places, in a place called Saskatoon. And it was basically a very different environment than at Langley or Oak Ridge. My uncle was my mentor. He was an electrical engineer, went to MIT and worked on the Manhattan Project. So it's kind of interesting that I wound up where the Manhattan Project is. But first I was at Langley and NASA Langley, and then Oak Ridge. Now I'm in Oak Ridge, and I actually am still affiliated with Oak Ridge because I have a badge good for 2 years, and the director's office asked me to do some tours. They have dignitaries that come by. So our tours are off now. We're not doing tours, but I'm working with a smaller company, Synective Labs. If you don't know about Oak Ridge, of course, everybody should, the Manhattan Project. They were basically enriched uranium facilities. On the right, I guess you can see my arrow. Over here is something called Y12. That's where the uranium was separated electrically by calutrons. That's what my uncle worked on. And Ernest Lawrence set up the facility, the ideas. And then my uncle, who was the engineer from Alice Chalmers, he was in charge of putting together the calutrons in big race car, 1024 in a loop to enrich the uranium. And then another alternative was to do it chemically, and that was over here. But Oak Ridge, we had the first pilot reactor that what was proved out and then went on to the Pacific Northwest Labs. So the first bomb to end the war was made at Y12. And the second one was from people here say, well, we didn't make it. It was the Pacific Northwest Labs, but really it was, the reactor was designed here to get the plutonium. Now, why I am connected is through something called parallel computing that I'll talk about, which is really the basis for computers nowadays. Back at Langley, I guess where most of you are, or maybe you're working at home, I was over in the building that no longer exists, 1229. That was my office right there. I'd been at several other 1148 and other things in the structures directorate. Now that building has been replaced by the computational research facility named by Katherine Johnson, who, if you saw the movie Hidden Figures, she was one of the prominent persons related there. Okay, here's Oak Ridge National Lab. It's a little different. You wonder, well, how can you go from one government facility to another? Well, everybody at Oak Ridge are contractors. They don't wear government badges like we do at Langley. So they're all contractors. So it's a contractor run facility that is rebid every 5 or 7 years. It's the World War II Manhattan Project, X10. It used to be called X10, just like there's Y12, but then they renamed it after the war to be Oak Ridge National Lab. And now it's where, oh, I forgot to say, the first picture was taken where the fastest computer in the world is. I won't go back to it, but right here, you can see a little turret with a number on it, and that's right over, I'm not sure if you can see it. Anyway, I'll move on. The X10, which was ORNL, was the pilot plant for the plutonium reactor that Enrico Fermi came down from Chicago and developed the facility. So it was the first place that there was nuclear electricity, generated for electricity. It was the first plutonium reactor. And like I said, it went to Pacific Northwest Labs. And my uncle worked on that with the Calutrons. Now here's looking up. This is what I meant by the turret over here. It looks like a turret, it's not. But it's got a number 3 on. The first picture you saw with the watered down sidewalks and so on was taken here. Right now, there's a whole new building here that encompasses Summit, which is the fastest US supercomputer right here. And I'll talk about Frontier that will be going into this building. They just cleared out Titan and are putting in the Frontier system, which will be the follow-on from Summit. Okay, and the building I was in, Future Technologies Group, is up in this building. And the picture out my window towards the reactor was looking over these parking lots. This is something about Oak Ridge Labs, the #1 energy science lab, 4,000 people, 3,000 guest researchers that come from all over, many from other countries. We have a hall of flags down here under the 3, and there must be 100 different flags from different countries that people are visitors. So it's an open lab, not like Lawrence Livermore or some of the others. We have the fastest supercomputer in the US. I'll talk about who's the fastest in the world later. And the National Science Foundation decided to house their computer here, as well as NOAA. And the US Air Force recently decided to house their new fastest computer. So we basically have some of the fastest computers in the US here. And they do that because the infrastructure has the people that know about the systems. Okay, and that's kind of like the budget. Okay, when you talk about supercomputers, it's a changing field. And now, when you go to supercomputing conferences, which there's coming up one next month in November, there's all kinds of, which 10,000 people traditionally go to, or 13,000 or something. Huge, huge conferences, biggest I've been to. And those conferences, they have sections on quantum computers, which is a big part of it now. And if you're aware, that's now making its ways into supercomputing. This is just an example of one computer. There's IBM, and I list all the other ones down there. So it's a huge research field. Now, as far as motivation, if you haven't had it so far, here's 2 books that are really motivating. And they talk about 2 people. One of them, Seymour Cray, is in the middle here. And he's really responsible for the origins of supercomputing, and the new supercomputer coming into the lab will be a Cray computer. The one we have now is Summit, is an IBM basically with NVIDIA, but the new one will be Cray. So his legend lives on. A great book to read. I read it, and it talked about his first job, which he said was on Pryor Avenue. Well, I happen to live on Pryor Avenue in St. Paul, Minnesota. I said, where in the world? And they talked about a glider factory. So I had to go up there and find it. So I found this glider factory, and it still was encompassed with the high security fence and all this. And I went in there thinking, okay, I'll just try it till somebody tells me to get out. And I went in, and they said, oh, other people have visited here. This is a very historic place where supercomputers develop. Anyway, you read that book and you'll see all you want about it. Now, that's the past. If you're interested in the future, this guy here, this is his high school picture. He went to high school in Oak Ridge. He went all the way through schooling in Oak Ridge. And then he went on to develop Siri for Apple. And he was the AI expert at Apple. He went on to Microsoft. He was the AI expert there, and Google. He was the AI expert. They asked him to start up a whole facility in China. And then after a while, he got disgusted with Google Set and Silicon Valley. He said, they're really too slow. We got to move faster. So he jumped ship and he's in China, but he was very grateful and came back and talked to the teachers in the school and the students and had a lecture. And it was a very interesting lecture. I got his book. It talks about the next 10, 20 years. So if you're interested in technology in the next 10 or 20 years, this is the book to get. You may have read this in the Washington Post. This is the most important technology contest since the space race, and America is losing. If you read that book or you hear his lecture, it's very insightful. One of my friends, from way back, David Wright, if you click on this quantum computing, and these slides will be online, if you click on that, you can get all you want to know about quantum computing. Okay, as far as the technical computer market, it's a growing market, and a big part of it is supercomputing, as you can see over here, 6 billion or so. And it started out in the government, like NSA and government agencies and some universities in the 60s. And then it moved on, so now it's just permeating all over. So the supercomputers are permeating our society from, you know, small companies. I don't ping for golf balls, Procter & Gamble. It's just all over the place now. So it's a tremendous market. Now I'll take you down memory lane as far as I was concerned. I have several pictures that show the computers as I see them. The first one I worked with, I was a physics major, physics, math, and we convinced, they got a new computer in our college, and some of us physics majors said, buy this Fortran compiler, even though it was business. So we got one of the professors to get the Fortran compiler, and we go in nights and get on them. And you wouldn't believe it, but back then, that was considered a technical trade, so to speak. So if you were messing with computers, it was considered not a professional or something worthy of spending time. But we loved it. And that IBM 1130 was a 16-bit machine. That was in '64. And each of these slides, I have things in the corner. The speed of it was, this is kiloflops, and flops are floating point operations per second, one like a 3.4 times 9.2. So 1,500 of those, and one processor. Well, then when I came to Langley, the fastest computer then was a CDC 6600. That was in 1970, and it had 500,000 floating point operations, which was astounding. People would come around to visit. This is phenomenal, and it has vector processing. We can stream things in. So we wrote codes, and you know, they were quite impressive back then. But then as the processors moved along, if the more you packed on them and made them tiny, there became more power, and then power meant heat, so that we came to a power wall. So what did it do? It splayed out to many processors, and at Langley, we recognized that and decided, let's do some experiments and develop a machine that had many processors, a multiprocessor, so to speak. And so we developed something called the finite element machine, and we actually built 32 boards. This is entirely at Langley with some contractors' help, just outside the gate. And so we developed that and ran it and showed that you could do this. And then we worked with companies. I particularly remember Cray. They said, one of the guys, one of my friends from Sandia, he said, you know, how are we going to convince Cray to go parallel? And so he actually left his job at Sandia and went up there and consulted. We worked together. Oh, my wife just put a note, moderate my talking speed. Oh, okay. Anyway, so Cray eventually got into the parallel processing. It took about 10 years, but eventually they got into it along with Intel. And we worked with those people and helped them a great deal. Now you can see they got up to 275 megaflops on their Cray YMP. Frontier, the machine coming into Oak Ridge next year, 1.5 exaflops. Now, exaflops. And you see the first slide was kiloflops. So what is the difference of exaflops and kiloflops? How much faster is the Frontier than the machine I first worked on? Well, an exaflop over kiloflops, fortunately still 1.5, So it's 10 to the 18th divided by 10 to the third. So that's 15 zeros, that many times faster. It's incredible. There's nothing on Earth I can know that has speed, you know, race cars go faster or whatever, spacecraft, but nothing has gone that far in our time. Now, how do you measure speed on these fast machines? There's something called the Top 500. If you go to top500.org, you can find all you want, including slides and presentations. And I've been at liberty to take several slides off of there in the future. They make things very good. July and November are the times that they run a benchmark, and they have like a contest every 6 months for around the world to see who can develop some results on their computers and, you know, new computers that are coming out. Jack Dongera, he just lives nearby here and works at university and consults at Oak Ridge Lab. He developed something called the Linpack Benchmark. If you look at this license plate, it says Linpack. That's back when he was in Chicago. And so he is the father of supercomputing, after Seymour Cray, of course. But he's part of the group that decides how fast the computers are going and the benchmarks and so on. Supercomputing, like I said, is coming up in November. And at that time, Jack and his colleagues will announce who has the fastest computers in the world. People have submitted their data, and then he goes through and analyzes it, oftentimes visiting the places too, to see if they're up to speed. The stars here, the supercomputer meetings I've been to. Fortunately, I went to Langley in '89. That was the second year they had supercomputing, and Langley didn't pay my travel. They said, this is crazy. We don't want to send somebody to a supercomputing conference. This is not a legitimate thing. So Cray said, we'll pay your way. So I went out and got their award because we were the first ones to get through the petaflop, no, not petaflop, gigaflop back then. That's 1 billion operations per second for space shuttle work. I'll talk about that a little later. The Linpack benchmark, you can read up on top 500 and whatever, and there's a new HPL benchmark too. Now, if you go to Apple, you can download a free thing, Linpack, and you can see how fast your phone goes, or your iPad, or your MacBook, or whatever. There's a fellow, Craig Hunter at Langley, that I think has the record for how fast he can go on a Mac, and he got 1.5 teraflops, astounding, on 28 processors on a Mac Pro. And when I take my my MacBook, I get a little bit less, and if I take my iPhone XR, which is already kind of out of date, this one here, it gets 21 gigaflops, which is you know, 20 times faster than when we got the Gigaflop award back at Supercomputing '89. So Supercomputing 18 at the top left here, we had a 30th anniversary of all the supercomputer meetings. So a lot of us were there, and it was fun to see how things change with time. Well, here, talking about changing with time, if you go, you can notice that every 10 years, every decade, the computing power increases 1,000 times, 1,000. So right there, you got 1 billion. And this was since we got the Gigaflop award, and that was for going through, we got actually 1.5. They wanted to get at least 1 gigaflop. We got 1.5 back in '89. And then Oak Ridge actually used a NASA machine at Goddard, and they were able to get 1.5 teraflops a decade later. And then here at Oak Ridge, one of my colleagues, Tom Schultness, who you'll hear about later, he was able to go through the petaflops. So that's 1,000 times 1,000 there, 1 million faster. And that was in 2008. And the next thing coming up is next year, 2021, we will have the next barrier, which is the Exaflop, Exaflops. And you can see the number of processors too. We basically had 8 processors on a Cray YMP. Then it went to 10 to the 3 processors, 10 to the 5, and now we're up to 10 to the 7 processors. If you don't know what an exaflop is, just look at the bottom here. And these slides will be online, you can look at them. Who's gonna have the first exaflop? Well, I think Any of these three companies are vying for it now. Japan, China, and the US. We'll talk a little bit more about that now. How do you, if you look back in time, back 27 years ago in '93, this is what the situation looked like. Now it's hard to understand this slide right away, but the red line down the middle is the fastest computer group moving along. And this is, you know, on a scale that goes by powers of 10 moving up. So it's really squashed down. So that's the fastest here. You'll notice there's kind of hiccups that go. And what that is, that's government funding that goes in and puts, you know, this is like 3 or 4 years, maybe 5 years, the government says, we want to have a fast machine. So they put money in and then they jump up. Recently, the Japanese jumped up to 416 petaflops. And if you go down to the bottom slide here, that #1 machine called Fukuta, it is 18%, a little over 18% of all the computer power in the top 500. Remarkable, 18%. So that is a huge machine. The one at the top here, the blue line, is the sum. So if you take all 500 machines that submit, you know, that's a big number there. And the bottom one, he's the guy that just barely made it. He was number 500 on it. So my iPhone can keep up with what it would have been on the top 500 in about 2001 or so. And Craig's machine would have been up there, and you know, I think he got somewhere in 2007, he would have been on the top 500 list with his Mac. Okay, let's move on to here we can see what are the important things in supercomputers? Okay, well, besides the main thing is called Rmax, which is the performance. So you can, whoop, I went too far. Okay, we'll go back. So you can see that in 2012, Oak Ridge Labs had the fastest machine, which they have had among American machines for decades. And the power of that was 8.3 megawatts. So you just look at that number, 17.6 for 8.3 megaflops. That's a factor of 2. Now the energy efficiency is 15 to 1 compared to that. So instead of 2 to 1 here, now we're 15. So the improvement in energy efficient, and I'll talk about why that happens. Now the thing circled here is the number of cores. These are like processors. So the machines, you'll notice, are going to have increasing number of cores through time. And then the horizontal things are accelerators. This has NVIDIA CPUs as well as these down here. So that's why Oak Ridge and some of the work that we did with accelerators brought our machines to the top. And so you can see the US was pretty much dominating them. And we'll jump a little later. What happened? Look at China. They came up with 2 machines that dwarfed everybody else. Here we are down with 8, and they're 18 and over 90. So that was a major impact. Then we regained it again at Oak Ridge in 2018. Here's the 2 Chinese machines, and we have another one at Lawrence Livermore. And then there's a big kind of a jump to the others. Then we come now, this is the latest listing. There'll be a new one coming out next month. But right now, the Japanese jumped up with their machine and 3 times what our machines are. This is Lawrence Livermore and Oak Ridge. I call this is Summit, Oak Ridge Summit. That's why it's not my initials, OS, Oak Ridge Summit. And here's the 2 Chinese machines that are down here. So this is how things have happened. The number of cores, I guess I have them. You can see this gives you exactly what you need to know here. This is the number of cores. As I said before, it was 10 to the 7th now. So so we're getting up there in the number of cores. At least the Japanese machine. Ours are here. Frontier will probably be more, even more. So and here's the Chinese machines. A couple things notice on this slide. The ones in yellow are people that never were even on the list before. They are new machines, nobody that came out, including one at NVIDIA in the US. But so we have number 2 and 3 right now, Oak Ridge and Livermore. Okay, that's where it is. Here's Thomas Schultness. He's moved from Oak Ridge over to the Swiss, so he's on top 10. Now, there's one interesting thing. You can run these machines in different precision. Mostly we use 64 bit precision, but there's a whole field of artificial intelligence that doesn't require that precision. So the new Japanese machine was really designed for a lot of artificial intelligence. So they made it so they can back off on the precision. So they exceeded 1 exaflop using their lower precision. So that's the first, you might say, the first time you're getting exaflops, but not true exaflops in 64-bit. Okay, and I mentioned about the power. Our power is 15 now gigaflops per watt. Remember, it used to be 2. So this is energy efficiency that is it really may, and I'll talk about why in a minute. So the top 3 are basically 15. The Chinese machines 4 and 5 are much less efficient, so it'll be harder for them to move up the scale. Here's the, I'm not going to go into detail, but this is the fastest computer now in Japan. It's basically half an exaflop. Now here's how they can adjust the precision over here and get those. If you want anything, you just click this, and Jack Dungera has all the information. He's been there, visited it. He knows all the details about their machine, where they're going in the future. Okay, some general trends. If you look at, well, the first thing you want to look at is the red here. You can see that, well, the US is blue, China is red, and you can see that the portion of the top 500 that are Chinese machines is really taking over. And you've seen that in the auto industry and other things in the past. Something to be concerned with probably in the US. Another thing is it breaks down to research and commercial. US is okay for research machines, Cray machines, Hewlett Packard and so on, IBM. But when you come to the actual commercial machines, most people, this Lenovo, which is now Chinese, and these Inspur and others, they're all Chinese. So the Chinese are basically taking over the commercial market. As far as processors that are used, it used to be there was an assortment of them over here, all the ones shown on the right, but now it's boiled down to basically everyone use the Intel x86 architecture. And that spills over into the software. So enable to use these machines, you have to have a lot of background in the different support tools from Intel, PGI, all of the accelerator companies like NVIDIA, and then you know, compiler support and so on. And these are all now wrapped up into a package that is like Unix. It's kind of free for everybody, not everything, but a good portion of it. So that dominates the development. You have to touch all the bases there. Now the application is the big thing, and I really should have called it supercomputing instead of supercomputers, because most of the work is really in getting applications to run on these machines. Now, Oak Ridge does not just get a machine and then say, hey guys, go and do something. It's like 4 years before, there's a team at Oak Ridge that says, we're gonna have a machine of this architecture 4 years from now. We want you guys to get applications that'll be able to run. And then we get some of the pre-compilers, we get some of the early hardware test bed things and get them running. I was on that team, and it's very exciting. You don't actually have the machine yet, but you see it coming downstream and work with the people that are developing the machines. So this is done, and it's decided up front which applications will run well on such machine. You want to spend a lot of time on something that won't. So these are some of them, and there's a list of pages and pages of all the applications that we work with. I'm just going to take one application, the one I mentioned, but Tom Schultness, who's in Switzerland now. But superconductivity was a big area. And at Langley, we had some superconductivity in the NTF and so on. But the theory of it was, there was some things that were missing, and it really had to be tested out. So you can test things in a lab, or you can do the theory, but the supercomputers can really dig in and get you the bottom line. So what you had to do when Tom was here he is, Tom Schultness, they had 4 physics people, very prominent physics people. Some of them knew software, And then mathematicians, computer science people, computer center people that knew the inner workings of things, and then the hardware vendors themselves from creating these. And was able to basically get to the bottom of how all the supercomputing worked, and they exceeded the 1 petaflops in their simulations of supercomputing, of superconductivity. Okay, it so happened in this process, I said it takes a long time before you get the new machine. Well, going to conferences, you learn a lot. And this guy, Bill Daly from NVIDIA, he's also a Stanford professor, chief scientist. We were presenting things at a conference over in Amsterdam. And so happened we rode on the canal boats and went to a facility, and I happened to be with him at the banquet, my wife and I. Fantastic guy. He's the one that developed basically the Summit machine from my point of view when I look at it, because it's really accelerated. 90% of the work is done on the accelerators, and the front end IBM processors are doing kind of the traffic cop, telling where to do the processing. He's a real sports car guy, and he likes to soup up cars and MGs and all these things. So he said, well, doing computers is the same thing to him. A very exciting guy to work with. But anyway, he basically announced how they're going to develop back in 2015, how they're going to do it, develop Summit. And the main thing I saw from his talk was that they had developed their architectures for what scientific computers are going to do onto chips, GPU chips, that when they ran the same thing on CPU chips or GPU chips, the power was 12 times less on their GPUs. That had a tremendous impact on supercomputing, because we used to have all these supercooling and all these archaic things. Now we can use regular cooling. You don't have to spend all that money on the cooling system. So that opened up the door in supercomputing. So they designed the Summit computer, the fastest in the US, for the best CPUs, IBM P9s then, and the Volta GPU, and the NVLink. Here it is, Summit. And I've got my Langley shirt on there, because I'd just been to the 100 years anniversary of Langley. Then they had an anniversary at the lab too. People that are prominent dignitaries, politicians, usually come and sign these machines. So the machines we have at Langley, if they're a fast machine, they'll have people come in that sign it. I can't even read the signatures, but they're probably people you know. Okay, that's the supercomputer part. Now analysis, that's really what these machines are for. Whether it's aircraft, spacecraft, automobiles, mechanisms like a aircraft deployment of the wheel. And I was in the structures group, and Nastran just was being thought about, kind of a gleam in the eye when I came to Langley. My first job was to compare the force method with the displacement method, which Nastran was. And I was able to get hands on Nastran early and become work with it. And we decided to go with the Nastran displacement method, as it looked very superior. And since then, it's taken over in many codes. It's based on finite elements that Ray Clough developed, of all places, in Norway. In fact, I highlight that here. He was a developer from Berkeley of the finite element method, although he spent summers up at Boeing and he saw what they needed. So he had a sabbatical leave in Trondheim. I also had a sabbatical leave over there and had some time to think about how to do it. So that's where he came up with at the university in Trondheim. So he saw the vision of the power of powerful computers from his time at Boeing, but he didn't do it alone. There was another guy, Jim Tosher, who's a computer guy from Boeing, and I knew him quite well. He was at Boeing. They had BCS back then. And so he was a postdoctoral fellow in Norway also, and he designed a way to make the finite element method go very fast. And then somebody else who was Ray Clough's student also developed an improvement of the element, and because the early finite element codes made a lot of difference. So what happened is that Ray Clough, Jim Tosher, and the refinement ended up to be the HCT element, which is shown on the left. In the old days, we used to just take plate elements and try to do it, but it wasn't very accurate and so on. But they came up with a triangle that was, you could take two triangles and it would be far superior to working with plates and all. So the finite element area was really a blossoming area. And now it's just all over the place as far as supercomputers. Okay, so the impact, in fact, this was from a contractor who worked on, Joe Glaudeman, who worked on MSC was his company. And he talked about at IEEE meeting way back about the impact of supercomputers and all the spin-off. You can see it here, that reduced the time, and it became the main structural analysis tool. It huge detailed models you could solve, things that you could never solve before. It extended into optimization, design, nonlinear, into artificial intelligence, widespread throughout the government and industry and academia. And it effectively can use vector, multiprocessor, and accelerators. Okay, so that's about the analysis. And this is not the main thrust. It's just, if you're from NASA and you're giving a talk and they find out you've been at NASA, they say, can't you add something in with NASA? So that's why I put this in. And I worked on the Viking. I was one of the youngest people there, and I had worked, like I said, on the finite element analysis, and that was one of the things I wanted to do on the Viking project. So I ended up doing the lander analysis, some of the orbiter analysis, and then I got into some work on when they had a problem with the GCMS box to house the instruments. So that was one of them. When people talk about when I work at NASA, that's the first thing I think of. It was a very exciting project to be associated with. And we have anniversaries. We had the 40th anniversary recently. I don't know how the time is coming, but I guess I don't have time to do the video. But if you see this, you can click on that and see the video about the Viking. It's pretty uplifting. Mel Anderson, I saw him recently at an anniversary. He was involved in the Viking project and actually saved the project. They had to stiffen up the aero shell, otherwise it would have been a disaster. And he recognized that and interrupted everything and then went on and had the stiffened panel. Dick Snyder made a lot of, he was my boss when we were working on the structures for the lander. I saw him recently. He was down at the Cape when the things launched. He was very much involved in the success of the project. And he's still in the Hampton Roads area. Okay. The GCMS gas chromatograph mass spectrometer, Litton Industries designed a box that failed. It leaked, and so had to have it 9 months before the launch, 9 months during the launch, and 9 months after the launch. And this thing leaked even before 9 months. So we had to design a box at Langley to incorporate the instruments on a very rapid base to make up the slack that would have been on the project, because it was supposed to be, you know, the video would show that it was supposed to be on the bicentennial, but it slipped a little bit to the July 20th, which happened to be the 7th anniversary of landing on the moon, which is another nice time. Anyway, when we went back to our 40th anniversary, the labeled release experiment, the guy in charge of it, Levin here, he claimed that, well, here's the slide that shows it, that they actually found life on Mars back there, but the other instruments like the GCMS didn't show that, and people kind of geared towards that. So now they're going to actually go back and check again and see that if you actually found it. Some of the work I did was on the shuttle, first with the wing tail structural analysis of finite element models before the Challenger disaster, and then after the disaster, we got involved in trying to speed up the algorithms to analyze it. And that was the result of this Supercomputing 89, the second year of supercomputing. Craig gave us the award at the Supercomputing conference. We reduced the time of analysis from 14 hours to 6 seconds, which was incredible. So in summary, I've showed you the huge supercomputer growth. It went through different eras, the vector era, multiprocessor, multi-core, hybrid, and so the past was the vector era, and that was 1 million times per decade. The present is multi-core with the Japanese Fugaku machine and the Summit. These are how many cores they have, 7.3. Summit is 2.4, but our frontier machine will probably be more. And then the future, the hybrid frontier. Couple things that are concerns in exascale is coding 10 million processors or cores in a fault tolerant. You know, you can have things that go down and you have to compensate for that. But that's being addressed. And then the power of the machines, as I said, it was a glooming problem, it seemed like, but now that has been solved because of the efficiency, like I showed you. Now, the NASA missions, I didn't say much about it, but those I've been involved with, it's really computationally oriented. We took over basically all the computing capability we needed at Langley, and then we even used the Air Force computer. I'd never been over there in those secret computers and used some of their things too on the Viking project. We just had a no holes barred. And so the rapid analysis and that's the key to success, not only before the launch, but during and after the missions to analyze all the data. So the supercomputers is really important in that. Okay, well, thank you for listening. If you have questions and answers or you want to follow up with me, you can do that. So I guess it's back to you, Rick.
Yeah, great. Thank you very much for that overview. That was pretty good romp through history there of supercomputing. So we do have one question right now. Let me remind everyone, you can either use the Q&A button at the bottom of the interface, or if you don't see that, there's a chat window as well. I can look at both of those. All right, so the first question says, will there always be a niche opportunity, or do you expect quantum computers to dominate in the future? So it's mainly centered around quantum computing.
That's a really good question, because I don't know. I think Dennis Bushnell is still back at Langley, if you know him. And I remember when we were working with supercomputers at Langley and coming up with new techniques using FPGAs and accelerators and so on. He was pushing hard and saying, Olaf, quantum computers are just around the corner. They're coming any time now. Why are we spending time on these accelerators? Well, so I had to contact my friends at NSA and some of the labs, and he said, write me a report that shows that quantum computers are not going to be here for 10 years, and I'll support your work. So I got this report, which is a secret type of thing that I gave to him that said that these aren't going to be useful in, you know, the imminent time. And it's always kind of like been the quantum computers are just around the corner. But the reports that I got back then basically said for floating point arithmetic and doing things like CFD and structural analysis, it's not going to be practical. Well, it seems like that's been continuing on, that all these things are, it's a hype thing and at supercomputer conferences, but the Chinese are getting into it, and not only quantum computers, but quantum communications from satellites back and down. So I talked to some people from NSA that were at supercomputing, and you know, they're kind of, you hear both sides of it. So it's something that needs to be addressed, but I don't think quantum computers are going to take over like in 5 years or something like that. It's something that is like more like research and experiment. I talked to people from Cisco at the meetings, and the quantum communication, they were concerned about that too, but as you can see, there's a lot of people working on it, but you know, just as, you know, I can't predict what's happening for sure. Nobody can. Nobody knows what people are doing in other countries, you know, the Chinese and so on. So I guess I have to hesitate to say, I just don't see that, you know, there's this big wave of quantum computers that's going to outdo everything else. But I think they're going to play a role. Now, here's another data point. If you read that book, and I asked the same question to the quantum or AI expert, the #1 expert in the world that came to Oak Ridge, and he, in his presentation too, he said that quantum computers are important, but the most important thing that is going to happen to us, every individual in the US and China, is going to be AI. That's going to dominate. Quantum computers are like 10% of that. It's not going to, so the big wave is AI. Quantum computers are something that are going to be there, interesting, research it, try on some applications. I think NSA will have a great performance, because they don't have to worry about floating point arithmetic and so on. They can do integer arithmetic in their algorithms, and so they'll probably have a heyday with the quantum computers. We have quantum computer access to most of the major ones here at Oak Ridge, and the people that I know in my group and others are working with them. And, you know, I see them all the time at church and whatever. And so, you know, we have things that we have in common. So anyway, I don't know if that's an answer, but I don't see them dominating and suddenly, you know, it's another thing that's on the computer floor and when you go to a supercomputer meeting. Hope that gives you a view. I don't want to be pessimistic. I'm optimistic about them, but I don't think it's going to just displace everything else.
Okay, there's another one specifically about the Cray 2 computer. Did the Cray 2 have much impact on supercomputing development? And this is from Steve Resnick. I got to do aerospace CFD dissertation research at Ames on the first in 85, 86. Is YMP totally different? Question mark.
We had a Cray 2 at Langley, and then we had a YMP we used at NASA Ames. And, you know, so they were both good machines. People were able to get gigaflops back then on the Cray 2 at Langley. And one of them, I guess he went up to the University of Virginia, Lambiot was his name. And he was able to get over a gigaflop on that machine. It's a remarkable machine. But the YMP pretty much took over after that. So you had the two lines, the Cray 1, Cray 2, K3, and so on, the number line they called it, and then you had the XMP, YMP, and so on. And Cray itself couldn't support both lines, so they decided to drop the number line and go with the distributed line. It was a decision they made. You know, being from Langley and working in supercomputers, I got to go and meet the people at IBM, and we take our algorithms up there. And I remember one day we were up at IBM, and they were funding the work that was done by Steve Chen. And so I pursued with them. And then later I went to a conference to present something, and Steve Chen was right after me. And it's a weird thing. You go to conference and, okay, here's Olaf's talk. Now that's over. And then we're going to take 10 minutes so all the press can come and everything. So then Steve Chen gave his stuff. But I'd heard from IBM before that they were going to pull the plug on him. And so it was interesting to see his talk. But that was one case where Boeing got in with IBM and went down the wrong way. It's hard to predict things that will happen, but it was quite a secret operation for those companies. So now I've I don't know if I've answered the question, the Cray 2 and the Cray YMP. I like the YMP, but I don't think it was that much of a difference, but Cray decided to go with that route. I don't know if that answers anything, but of course there was the company called, after Cray's initials, SRC, Seymour Randolph Cray. And that was the last company he had, and that was out in Colorado, and he decided to pursue the things that we were doing and in parallel computing, and to a big degree. But of course he had his auto accident and died and whatever. But SRC continued on. I don't know if they're still in business, but that was kind of the last hurrah for that. Yeah, there's a whole history. And when we went back to the 30th anniversary of supercomputing, they had a Cray there, and all the people they were soliciting to come that remembered the old days, they had all the architectures and all the hardware sitting there you could look at. It was just like going to a museum. It's a fascinating thing. And we had a group at Langley, the supercomputing group, which was really fun. We'd have meetings and talk about all the future things that were happening and have conferences with Ames and whatever. Very, very exciting. I don't know if I can portray how grateful I am for having the opportunity to be at Langley to work with some of the state-of-the-art things and really top-notch people. Intel too. I was on a board with Intel for many years, and they would tell us their new stuff coming down. I got a machine that was the first one that anybody got their hands on. And that was very interesting. One of the new processors they had that they wanted people to test it out. I said, yeah, I'll test it out. So yeah, I think the future is even more exciting because there's so much that's happening that in the hardware and electronics that is going to impact us. But a lot of it will be algorithms now, and AI algorithms. So if you get that book on supercomputers, or read Superman and the one on AI, those two books are very, very exciting. Okay, I don't know if that's answered it.
Okay. Yeah, so you were mentioning there about algorithms, and you talked about Linpack and maybe some other testing algorithms. So do you think Linpack's here to stay in terms of measuring performance, or is there going to be different types
Oh,
of ways to
oh,
measure performance?
oh no, Linpack is probably now, it's carried along, but there's the HPL and there's the Linpack, there's green machine algorithm, there's probably 10 different algorithms now. And so Jack's group has all of these. And if you go to the top 500, you'll find all the other things. But the Linpack has been around for a long time, and it's basically solving a system of equations. And the idea behind these algorithms is to give a snapshot of how they can perform. So if you're going to go and buy a supercomputer, how is it going to perform? Well, the thing is, some algorithms are going to perform differently than others. So you need a suite of different algorithms to, and NASA Ames got involved in that too, and Horace Simon. So there are a suite of algorithms. So if your machine is for AI, you don't want to use Linpack to benchmark which machine you're going to buy. You want to use the AI benchmark, like the ones that the Japanese machine performed so well on. And some of the accelerator machines were kind of left out because they did not perform so well on some of the early Linpack models. So that is a changing field, but it's hard to go away from an existing measurement because everybody knows Linpack and you can run it on your Mac or your phone, but the other ones are more specific. But right now, if you talk to Jack, I think he prefers some of the other algorithms, and so they report results from multiple algorithms now, but they seem to always have Linpack there because that's kind of like a benchmark that everybody understands. I like it because you can run it on your Mac, and and I contacted Hunter, and he sent me his Linpack for the Mac, which, you know, it's fun to just see how different machines perform.
Okay, and there's one more question. I don't necessarily want to end on a kind of brooding note, but the comment here is just saw the video, The Social Dilemma, and it was a video, I guess, about AI and privacy and painting a bad picture of it. So I don't know if that's a ominous note to end on or not. You have comments about that?
I think that's very important. And when I went to hear Lee's talk, it was in our Oak Ridge big civic complex, and it was standing room only, and you know, even lab people couldn't get in. It was just and I was astounded, but I sat right up front with my wife and we talked to him after extensively, and I asked a bunch of questions in there too. And one of the questions was, you know, the Chinese are very acceptable to having cameras all over, and to have data collected and all this. And so AI just spreads out all over. They don't have any problem with that. Of course, here, that would be a different story. All we'd have lawyers fighting this, that, and the other thing. One example, just to give you, is he said that over in China, you know how we have people in banks that approve mortgages, that approve loans and all this. He said that stuff's awful obsolete. Over there, they have 500 or so criteria that they get immediately from their data system that tells if somebody should get a loan or not. He said you can walk down the street with your phone, you can enter all the data, and you can get your $30,000 right then. Of course, maybe, I guess they advertise on TV you can do that, but that was basically AI that looked at things. Now, what do they look at? He said, well, it's a bunch of the standard stuff. But something else they look at is how many times you leave your phone on, so it goes down and loses its battery. There's a what do you call it, a correlation between people that leave their phones going dead and people that are reliable on returning loans. Who would have ever thought of that? But that's just one criteria. So they have all these different criteria that do that. So it is a tremendous invasion on privacy. You know, you don't want people to know if you let your phone go down or not, but so it's a whole different concept. But he said AI will just spread like mad in China and probably not here. So we'll end up being behind to preserve our policies of data and that type of thing. But I mean, who's right or wrong? I guess I'd say we're right, but on the other hand, you hate to see some somebody taking off. But on the other side, as far as crime and criminals, they have a ranking system so that when they look at this criteria, they can prevent people from getting an airplane or a train, or, you know, you basically, instead of going to prison, you're just pushed down on a scale and then you have to work your way back up again. So that's a way of confronting crime without putting people in jail. So it's just minimizing what they can do in their society. It's a very interesting book to read. I recommend you do it, and it'll make you think about some things you never thought about before. I mean, we can continue to do all the things with the computers and AI, but it can be misused. And then who's going to decide if it's misused or if it isn't? Yeah, it's a very good question. And I don't think it's a question that is a downer. I think it's a question that it opens up doors to things you never thought of before. And he's a fascinating person to talk to. I think it was great that he came back and talked to all the schools and the teachers where he had been, and gave lectures and little seminars at each of the schools, the grade school, the middle school, the high school. And he had people coming back from his high school, and they all got together. And yeah, so, you know, he is an amazing guy. And he has faced cancer. In his book, he talks about that. And so he kind of changed his view. And I thought that he said many things that were not necessarily pro-China. So he has experienced the Western life and he's experienced our life, and he can merge the two. And I don't think he fights the Chinese government, which, you know, a lot of people wouldn't do that. So I had some sympathy for, you know, in talking to him and what he said. By the way, he said that he doesn't even use a credit card. He said credit cards are, you know, they're out of date. There's no need for those anymore. That was something I didn't know. And people, you know, came up after, how come you can't, yeah, he said, I don't need, he took out his wallet. I don't have one. I don't need one. What do you use? Oh, I use my phone. He could do everything on his phone. No need for credit cards. I mean, that's a pretty different philosophy from what we are. We have loan agents. We have our credit cards and all this. So it's good for us to think about what other possibilities are.
Okay, great. Well, I think we're at the top of the hour. That was a fantastic seminar. So we really appreciate your presentation today. Just a reminder to everyone, we are recording this and we'll be posting it on Engage for the AIAA website. And you should have access to that and his slides. And then in the flyer, I believe it had the link to his website with his other material. So with that, I'll say thank you. And thanks for everyone for attending today.
Thank you very much. I appreciate it, Richard. It's fun to talk about things that are in the past and in the future.
Yeah. All right. Very good. Thank you.
Bye-bye.